I'm noticing as things get harder, I'm taking longer to talk about them, and so I'm increasing. I really have to figure out, I have to bite the bullet and figure out how to free up my RAM memory, my memory card, so that it has access to 32G and not just 7G, because I'm now regularly running out of memory by talking too long as the stuff gets harder. But I hate looking at manuals, so I'm demotivated at the same time. But I just have to. This is happening like every board now. Okay, I have 32 minutes, so I have to finish this one within that time. Otherwise, the camera's going to stop. Okay, so let's try to do it for 0 steps, because that will work. Now, what are we trying to show? We're trying to show that if the machine goes from state P reading substring X, it'll end up in state Q, right? And from that, now if that's the case, then the equivalent grammar G, its variable A, big A, PQ, will generate the string X. Okay, I think that's yes, right. And we're going to and the integer in this inductive proof is the number of steps in the. Okay. It's the machine's number of steps, where each step would be like reading the next symbol in the input string and changing the state. Okay, so let's start. It's an inductive proof, so it's a two-step. So let's start with the basis part, and let's start with 0 steps. Okay, it doesn't do any steps. So what happens then? Well, if there are 0 steps, the machine cannot change state, right? So it just stays in the state that it was at, and so the final state is just P. Okay, so it goes from state P to P, and so we have to show then that when it's in the same state at the end, so initial state little p and final state little p, that this variable produces an x that would be the same for the machine, right? I mean, the whole point, we're trying to show that this grammar behaves the same way as the PDA, right? So now for the machine, when there's no state change in 0 steps, the only thing that the machine, big P, that it can read in 0 steps is the empty string. Okay, so in other words, the x that it's reading is just the empty string. So you'll need this to be x here. So if x is the empty string for the machine, for the PDA, you want the grammar to behave in the same way, right? That's the whole point. So you'll want this x here, when it's pp, to be eta. Sorry, I keep making that mistake. Epsilon. Okay. So you'll want the grammar to make the substitution. To derive from a pp, you want it to derive epsilon. Well, that rule is in the grammar, right? In fact, we put it into the grammar just for this reason. So, like I keep saying, go back and forth between the proof and as in the first. Well, you can't see it now, but in the first board, we had all the. The recipe we used to put rules, substitution rules, into the grammar. Okay, now you're starting to see why we put in rules of that form. Okay, so that agrees. Okay, so we've done now the basis step for our inductive proof. Right now, now let's do the induction step. So we assume that okay, now we have more than 0 steps. We have several steps, let's say, and the machine, the PDA, goes from state little p to state little q in reading that substring x, and we have to show that the equivalent grammar that we're generating will recognize the string, the same string, x. Okay? Alright, so let's choose okay, so we're now we have a string now x, and we go and we read that x, and the machine, PDA, goes from state little p to state little q with empty stacks here and here, but it does that in k plus 1 steps. Okay, our integer now is in terms of the number of steps in the machine, in the computational process of the machine, and we'll assume there are k plus 1 steps. Each step, remember, the machine, it looks at the next input string symbol and changes its state. That's 1 step. Okay, and we're assuming now it's reading this and it's changing from this to this, both with empty stacks, and it takes k plus 1 steps to do that. Alright, now again we have the 2 cases. The stack can empty only when it, at the end, when it goes to state q, or it can empty prior to that, so it will empty twice or 3 times, anyway, more than 1 time. Okay, then we have those 2 cases. So we'll treat each case separately. Now, in the first case, that's when the stack clears for the first time at the end, when the state goes to, when the machine goes to state q, right? Okay, so that means when that happens, the symbol that you pushed at the first move, like the first step in the PDA, that it must be equal to the symbol that you popped at the last move, right? I mean, you can look on that symbol as like the $sign. The behavior is the same. That symbol that you first push, and the stack has not cleared, right, until the end, and your last move is a pop. Well, if the stack hasn't cleared before, that last pop clears the stack. But what now? That's last out. But last out in a stack is first in. Well, what was first in? Well, the first symbol you pushed. Okay, so the first symbol you push and the last symbol you pop have to be the same. Sort of like the $, right? Okay, so now call that symbol little t, right? The one that has to be the same. The symbol you push and the first symbol you push and the last symbol you pop has to be the same, and that symbol, input string symbol is